So if you want to find the increasing decreasing interval, so first of all, you need to figure out the critical points. So last time we discussed about the critical points. So first you need to find the domain of the function. Okay. So first find the domain of the function f. Once you have domain, so take your real line and identify your the domain. After that, so we find the critical points, right? So you find the critical points. For instance, say you have critical points C and D. So these you divide the entire domain into a couple of sub intervals based on your critical points, right? So after that, suppose C and D are critical points, so you will chop off the given interval into sub intervals with open intervals. Now after that, remember in the critical points, the slope is either zero, right? Slope is either zero or does not exist, right? So you have to figure out, whether the function is decreasing in these subintervals or increasing. So how do you identify those things? Simply we use first derivative things. Okay, so that's what is explained here. So if you find the first derivative, or in that interval less than zero, negative, then the function is going to be decreasing. And if you have the first derivative is positive in that particular interval, then the function is increasing on that interval. Okay. So we make like this table to find the increasing, decreasing interval. So we already discussed these things last time, I believe. So first take the interval, divide into subintervals, and take some test value in each interval, right? Then plugging those test values into the first derivative and check the sign. If you are getting positive, then function is increasing. If you are getting negative value, then function is decreasing. Okay. To identify the function whether it is increasing or decreasing in the given interval is enough to check only a single point. That is why we call this as a test value, right? So simply you pick one value. You could pick any value in this interval. It's up to you. Plugging that x value into that first derivative function, then check the sign. If it is positive, increasing. If it is negative, decreasing. Okay. So you could go through my worked notes. So there I have worked plenty of problems to get understanding, better. So follow these steps. So now this is the guideline. So we use to find, the function is increasing, decreasing. What are those? First, identify the critical points, then divide the domain into subintervals by using those critical values. Then you have to find the sign of the first derivative in each interval. So if we get positive, it is increasing, and if it is negative, which is decreasing. Okay. So this all about finding increasing, decreasing function. Okay. Now next one is called the first derivative test. The first derivative test we use to identify, you know, the function has a relative maximum or minimum. Remember the definition of relative maximum minimum? If you take a small open interval, so if you could find any minimum value or maximum value of the graph in between that open interval, then the function has relative minimum maximum. So last time we discussed about existence of relative maximum minimum. Do you remember? We had one theorem, right? Relative maximum or minimum always occur at the critical point. Okay, so that's why critical point is very, very important to determine whether the function has a relative max or relative minimum. Okay, so this test says what? How do you check whether function has relative max or minimum at the given critical point? So you see now, to check the function has minimum or maximum at the critical value, what you want to do is take the interval, open interval, which contains that critical point, then figure out the first derivative just before and after that point. Okay, remember our task is to find whether function is having maximum or minimum at this point. Okay, to check that, you find the first derivative just before this point and the first derivative just after that point. So if you look at this scenario, this example, we have negative slope and the positive slope. Remember, here we had negative slope means function should be decreasing, right? That is why you see the function is going down. Here, the first derivative is positive, so function should get increasing, trend. Remember, at the critical points, the slope is always going to be zero, right? Or does not exist. Here we have taken all four scenarios where slope is zero. So this slope is zero. So the only way is function attains minimum, then increasing. Therefore, we have relative minimum. Okay. So if you want to get a relative minimum, simply you have to have first derivative minus and plus. Okay. If you look at the second picture, again, we are checking whether function has max or minimum at this critical point C. Again, you are checking just before and after the first derivative. Now here you are getting positive and negative. That means positive means function should go up and getting slope zero and going down. So if you have plus minus order, that means function has a relative maximum at that point, at that critical point. Okay, so you could use this first derivative test. But if you do not have these two orders, then function, does not have any kind of relative extremum. Okay, look at this case. Just before positive, just after also positive. So same sign of the slope. That means you will not find any relative max or min. Same thing here for the negative. Okay, so these two functions are, neither having relative minimum nor relative max. So only these two are the two scenarios if you have a minimum or maximum. Okay, so follow those guides. Okay. So if you look at this problem, so the question is finding relative extrema. That means you are finding relative maximum or minimum value. So what are the procedure? First, you need to find out the critical value. So critical value means what? You need to find the first derivative, and you are looking for the points where function is slope is getting zero or does not exist. So we take the first derivative of this function, right? The first derivative of half x is just half and sine is cosine, setting into zero, and you are solving for possible x values. Remember, we are interested in this interval 0 to 2 pi. So you are finding some x values in this interval, right? So we know how to solve the trigonometric equations. So cosine x would be half in this interval 0 to 2 pi. Of course, the possible values of x are pi over 3 and 5 pi over 3. So these are the critical numbers. Remember, my first derivative function half x minus cosine x is well defined, right? Well defined throughout this interval. Therefore, this function is well defined. First derivative is well defined. Therefore, you will not find any does not exist points. So only critical points will be, occurred only at slope 0 points. That is why we have only these two. Okay, so they are explaining in that here. Once you find the critical points, right? So remember, take your entire, sorry. So look at your domain. My domain is now, this is the domain for the given problem 0 to 2 pi. So take your real line 0 to 2 pi. Okay, so first we have to take your domain. Now locate the critical points. We have two critical points, pi over 3 and 5 pi over 3. Where are those? So pi will be somewhere here. Remember, pi means 180 degree, right? This is 360 degree. So the first critical point is pi over 3, 60 degree will be somewhere here. Okay. The second critical point is 5 pi over 3. 5 pi over 3 is bigger than pi, right? So 5 pi over 3 is how much it is? It is 300, all right? So that is somewhere here. Okay. Now what is your task? Now your task is to divide the entire interval into sub intervals like this throughout that critical point. So only you have to split the entire interval by using the critical values. Okay. Therefore, the entire interval 0 to 2 pi is now splitted into 1, 2, 3 pieces. This is my first interval, this is my second interval, and this is my third interval. So now take one value to test the f first derivative. Check one value with this one. Okay, you could choose any value between 0 to pi over 3. That is up to you. So here they have chosen that value as a pi over 4. First test value in this interval. Okay. Now go for the second interval. In second interval, pi over 3 to 5 pi over 3. So they have chosen pi as the test value. That means this guy. Then in the third interval, they have chosen test value as 7 pi over 4. That will be somewhere here. Like that, choose some values. And you could use either calculator or any kind of software to figure out the first derivative values. Remember, my first derivative function is here, right? So my first derivative for this problem is half minus cosine x. Now plugging these all three test values into this function and check the sign, whether you are getting negative or positive. Okay, so we are simply plugging pi over 4 into this function. Remember, cosine pi over 4 is, what is that? If you're plugging pi over 4 here, I will get first derivative evaluated at pi over 4. Simply plugging here, pi over 4 will be half minus cosine pi over 4. That is half minus cosine pi over 4 is, what is that?
Square root of 2 over 2.
Square root 2 over 2. Very good. Now take your calculator and simplify. Check what kind of number you get here, negative or positive number.
I got a negative number.
Yeah, very good. So you will get negative number. I don't want number. I need only the sign. So you are getting negative value. That is why sign of the first derivative at this interval is negative. Okay. Now go for the second test value. So again, plugging this value into the same function, first derivative function. Now we are plugging pi here. So cosine pi will be negative 1. So that negative and this negative will be positive 1. 1 plus half is 1 half. So you will get positive value in that interval. Again, plugging 7 pi over 4 into that first derivative function, you will get negative. Okay, that's it. So now you know the trend of your curve, right? So what is that? That is in first interval, it says that you get negative slope, therefore it is decreasing. And the second interval, it is increasing because of positive slope. Then here you have negative, again decreasing. Okay, so decreasing, increasing, decreasing. So you have to write, final answer is like, therefore you have to write to what are the intervals you are getting where function is increasing, then write down the interval for decreasing. Okay, so for this problem we are getting only one place where function is increasing, which is you have to write in interval notation. They are asking you to find out the intervals. Okay, right? So okay, so you know now, right? So where is increasing, decreasing? So it is decreasing, increasing. So you could write down those if you want here. So I'm writing increasing is here, decreasing in two intervals, 0 pi over 3 and 5 pi over 3 and 2 pi. Okay, keep that. So we are finding relative max mean, right? Okay, so what I used to do is I used to, you know, marking the function trend here on the interval, right? Remember, in first interval we got decreasing, right? So I'm simply will put here, I'm putting here negative decreasing. Here in this interval we are getting positive sign. In this interval we are getting negative sign, right? So how your curve is going to be? So negative means, of course, slope should be negative. So your graph should be going like this, right? Right? Negative slope, positive slope, negative, positive. Positive slope is going upwards, negative coming down. So you will get minimum here. So if you draw the picture for this interval, right? So now go for the second critical point, this point. At this point, again, here we got positive, right? So therefore your graph should be like this. And this point will be negative slope, so it should be going like this. Therefore, at this critical point, function should have maximum. So here max and here min. Therefore, you see the curve now. So you could use the online tool to check your answer whether correct or wrong. So here max, here min. So they are asking you to find out what kind of extreme point you will have. Okay. Therefore, my answer is what? So you have to write in clear way. Okay. So we know now at this point, at this critical point, function is having. At this critical point, function is having minimum. So you have to write clearly. Therefore, relative minimum, okay, will be at x is equals pi over 3, my first critical point, right? So this is just a point where you get, relative minimum, but this is just the x coordinate of the function, right? You need to find out y as well by simply plugging this x coordinate into your function and find out the y coordinate as well. So if you're plugging pi over 3, where you want to put? You want to put into original function, okay? So your original function is here. Go back and check. Your original function is half x minus sine x, okay? So half x minus sine x, this is my original function. So you need to find out the minimum value, function value in another word, simply plugging here pi over 3. So that will be what? So that will be half pi over 3 minus sine pi over 3. Okay, so you will have now decimal points values. So sine pi over 3 is square root 3 over 2. So this is your minimum value. Okay, this is the point where you have minimum, right? The coordinate. So if you look at the picture now, x and y coordinates are here for the first point. Okay, where is that? Could you locate this one? That is somewhere here, right? Right? So the x coordinate of this point is now pi over 3 and y coordinate of that function is this. So if you check this value, should be negative, okay? Should be negative. So could you check please how much you are getting for this in one decimal please? Pi over 6 minus square root 3 over 2.
I got negative 0.34.
Exactly, negative 0.34. So this is the minimum value at that point. That is why you have a negative value, right? You will have here somewhere that value. Okay, this is our y value, the function minimum value, that is negative 0.34. This is the x coordinate of that point, which is pi over 3. Make sense?
Yes.
Yeah, very good. In similar way, you could find the relative maximum coming plus minus order. So if you are not clear, you look at this first derivative test. Plus minus means maximum, minus plus means minimum. So plus minus is maximum. So the second point is my maximum critical value point, which is 5 pi over 3, and again do the same thing. So maximum is here, 5 pi over 3. If you're plugging that value into function, you will get relative maximum. So relative maximum, remember you have to find out that value, okay? Like this. So relative maximum, okay, that is having at x is 5 pi over 3. What is that value? Value is y, which is f of 5 pi over 3. Okay, again take the function and plug in 5 pi over 3. So you will get 5 pi over 3 minus, oh, we have half there. Half times 5 pi over 3 minus sine 5 pi over 3. Let's say who is telling what is sine 5 pi over 3 without calculator.
Did you ask for the decimal form or did you ask whether
I,
it was on decimal?
I need the exact value like this without calculator.
Oh, okay. It's negative square root of 3 over 2.
Why it is negative?
Because it's in the fourth quadrant.
Very good.
Yeah.
This is in fourth quadrant. You are correct. So this is pi over 3 is 60. 60 times 5 is 300, right? So sine 300 is going to be in fourth quadrant. Sine is getting negative. Therefore, it is negative square root 3 over 2. Now you could plugging everything into calculator and find the decimal answer. Now you should get positive answer, right? Because you see now maximum value will be somewhere here. You should get somewhere 3 point something. This is the y value of the maximum, the function value, maximum value. So figure out that value. So this is going to be your answer, relative maximum answer. This is your relative minimum. Okay, so that's very, very, understandable. So follow those guides. Okay, follow those guides to find the maximum minimum. Okay, so you have plenty of problems here to check and make sure that you understand all the steps. Now here in this problem, you can use the graph utility and draw the picture and check whether this answer is correct. Okay, so this is the work now I am leaving for you guys. So make sure that you graph this picture like this. Okay, check. So this is all about finding relative max min by using what? First derivative. So that is why we call this as first derivative test. So let's move on to the next one, 3.0. This is about identifying concavity of the graph. So what is the definition of concavity? So if you read here, the concave up function is always going to be facing upwards like a cup, right? So if the curve is facing upwards, so we could call that as a concave upwards. Okay, so if function is facing down, then we call that function as concave downward. Okay, so now the thing is, how do you identify whether the function has a concave up or concave down? So we have again a couple of tests to check whether function has a concave up or down, like first derivative test. Okay, so if you look at this picture carefully, for concave up, what's happening? If you find, the slope at those tangent points, or tangent curves, in other words, when you increase your x, right, you look at the slope value. In another word, the first derivative is increasing, right? The slope value is going upwards, right? First slope is almost very close to -0. But here the slope is positive value. Here you will get positive but bigger than this value. So for concave upwards trend, first derivative should be increasing. Okay. For the concave downtrend, if you look at the slope, now slope is going down, right? Slope, I'm talking about the slope, first derivative. So for concave downtrend, function should have, the f prime, the first derivative should be decreasing. So keep in mind these two very important points to determine whether the function has concave up or down. Simply look for the first derivative, whether first derivative increasing or decreasing. Okay. So what is this? This is another way to check, right? So if all the tangent lines are, below the graph, or graph is above the tangent line, look at that. The graph is always above the tangent line. So then in that case, you will have concave up. But here in this picture, graph is under the tangent lines, right below the tangent lines. Therefore, this is concave down. So now, in either way, you could, or memorize the way to find the concave up or down. Okay. Now, look at here. Look at these two pictures. Remember my original picture. Our task is to find the concave up or down for what? For original function f(x). Don't confuse, okay? Our task is to find the concavity of what? Of the original function f(x). To find out that, we simply check the first derivative, okay? No confusion. So we use first derivative to check about the function strength, okay? So no confusion. Our task, ultimate task, is to find for function, not for the first derivative, okay? So now if you look at these two pictures, the original picture is here, right? fx. So if you look at this picture, from this point to this point, function has concave downtrend, right? After this point, you see now the concavity is turning in another way. From here to all the way up to this point, function facing up, concave upwards, right? So what does mean by that? If you find the slope, first derivative for this function from here to here, that should be always negative, decreasing, right? That is why when you find the first derivative of this function, what is the first derivative of this function? F prime x, simply the first derivative of x cube, which is 3x squared, then subtract 1. So if you simplify, you will get x squared minus 1. So now this is my slope function. You could think of this as a new function, x squared minus 1. So if you plot that function, that is somewhere here, right? So no confusion. This is the graph of f prime x. This is the graph of the original function, okay? So now this picture gives clearer, the picture about the connection between the concavity and the first derivative. From here to this point, right? You see now, my f prime x function is going down, right? Decreasing, decreasing, decreasing. Up to this point, f prime x is decreasing, right? We all know now, if f prime x is decreasing, so you will have concave downtrend. That is why for the original picture, we have here to here concave downtrend. Okay? From this point to all the way here, my first derivative is getting increasing, getting larger and larger from here to there, right? My first derivative is now increasing in this region. Therefore, there you will have concave upward trend. You see now the connection between first derivative and your concavity trend of the given graph. So make sense?
Yes, sir.
Okay. So where's William? William right here. This is another test we use for the concavity. Okay. Please follow these steps. If you want to find the concavity trend, first take the function, okay, identify where the second derivative getting positive or the second derivative get negative. Look for the interval for these two, okay. Why we need a second derivative? Remember, For the concurve up, our first derivative function f prime x should be what? For concurve up, our first derivative function should be increasing, okay? So that means for the concurve upward trend, first derivative should be increasing, right? You could think of this guy as my new function gx if you want, right? You could think of the first derivative of f as your new function gx, right? So I'm asking in another way. If gx is increasing, of course, we know now, right? G first derivative should be positive, right? Like in previous section, we know that if gx is increasing, that means the first derivative should be positive. That means what? That means if f prime x is increasing, then if you take one more derivative of this guy, that is my g prime, which is my second derivative, right? Should be positive. That is why it says, right? So this is another way to check concurve upward. You could think of with first derivative or the second derivative. First derivative mean it should be increasing. In another word, if double derivative should be positive in that interval, throughout that interval. Okay, so keep in mind these 2 points. So this is another way, vice versa. For concurve downward trend, your second derivative at in that interval should be negative. Okay, so you have to find a break-even point where function getting second derivative getting 0 points. Okay, like we did earlier. Remember, if you want to find the relative max minimum, we did just now in 3.3. We found the critical point by setting first derivative to 0, and we splitted the entire domain into small subintervals, and we found function has a minimum or maximum. In similar fashion here, what I'm doing, I am now setting second derivative as 0 and identifying the points where your entire domain is splitting into subintervals, right? So you have to find the points, look for the points where second derivative getting 0. After that, now you test the value for for the second derivative. Okay, whether it is getting positive or negative. If it is positive, then concurve up. If it is negative, it is concurve down. That's it. Okay, so now let's think about with this problem. So the question is now, you need to identify the intervals. You need to find out the intervals where function has a concurve upward trend or concurve downward trend. So what is my first step? First step is to find points where function getting 0 at second derivative. Okay, so I need to know now second derivative. So take the function, find out the first derivative, then again one more time take the derivative of that function to take the second derivative. This is our second derivative, but simplify that one. If you simplify that, do some algebra, you will get this. Okay, so our second derivative it says, which is 36 times x squared minus 1 over x squared plus 3 all the way 3. Okay, now set this guy to 0 and look for some x values. Of course, if you want to make this guy 0, only possible way is the numerator supposed to be 0. Solve this guy. So this will give you x squared is 1, therefore x is plus or minus 1. So these are the two values we are getting now where second derivative getting 0. Okay, before that, ask yourself, what is the domain of this function? Could you tell me the domain of this function?
Let's see, because it's x squared plus 3 and you solve it for 0, that means your x can't be either of the 3's positive or negative.
Okay.
So wouldn't it be negative 3, 3? Wait.
Okay, my question was finding domain, right?
Right.
Okay, what does mean by domain? Domain means the points where function is well defined, right?
Right.
Okay, that means what? If you plug any real x value, function makes sense. You will get good number here. Am I right?
Mm-hmm.
Why? Because your denominator is always positive. Doesn't matter whatever you plug here x. X could be 0 as well, but still you will get the denominator as positive number, right?
Mhm.
So therefore, this function is well defined for any x value. So domain is good for any real value, all the way, negative infinity to positive infinity.
Mm.
Okay, so my domain is now negative infinity to positive infinity. That makes sense?
Yes, sir.
Okay, good. So now, remember, we had 2 points where second derivative getting 0. Now take your entire domain for the problem, negative infinity to positive infinity. 0 will be somewhere here, positive 1 is here, negative 1 is here, right? So 2 points are now, sorry, negative 1 and positive 1. So now, split the entire interval into sub-intervals by using these two, points. Therefore, this is one of those intervals, this is another interval, and this is the third interval. So now you have three sub-intervals. So entire real line is now, split into three sub-intervals. So again, take the test value for each interval. So that is why if you look at here, you see now the interval. So negative infinity to negative 1, negative 1 to 1, and 1 to infinity. So you have three sub-intervals, open intervals here. Now, like we did earlier, you have to test, take the test value for what? For the second derivative now. Okay, so this is up to you. You could pick any number in this interval. You could pick if you want negative 100 as well, no problem. Okay, now you have to look, the function, second derivative function value. So first of all, you write down here your second derivative function. Remember, this was my second derivative function, right? 36 x squared minus 1 over x squared plus 3, raised to power 3. So this is your second derivative function. Now you have to plug in your test value into this function and check the sign. So if you're plugging negative 2 here, you will get f, double prime of negative 2, simply plugging negative 2, okay? And check whether what kind of sign you have. So you should have positive answer here. Yes, it makes sense, right? Because this all, you are plugging negative 2, but this is square, so you will have positive. This will be, of course, 3 if you're plugging negative 2 here. So ultimately, you will get this as a positive number. Therefore, you will get the second derivative positive throughout this interval, right? In the second interval, we pick the test value as 0 because 0 is contained in this interval. So second derivative evaluated at 0, plugging 0 again into this function. This is 0, this is 0. So you will have now negative in the numerator and positive in the denominator. Therefore, ultimately you will get negative sign. Okay. Now plugging the test value 2 into this function one more time, you will get, which is positive. That's it. So in this interval, I'm getting second derivative positive, therefore concurve upwards, negative, concurve downward, again positive, concurve upward. Okay, so this is our final results. They are asking us. Okay, so your conclusion, if you want, you could write in words. Okay, concurve upward, write down the intervals. So I got two intervals. That is my first interval and the last one. My first interval is sub-interval is negative infinity and negative 1, and the last interval is 1 infinity. So concurve downward trend is of course on the one interval, which is the second interval, negative 1 and 1. So finally you have to write like this. Okay, so now after doing this all work, you could graph it and check whether you get correct answer. This is, the graph is simply to justify your answer, right? They are not asking you to draw the graph. This is just to simply check your answer. So you could use the online graphing tool and check. Yes, makes sense. Look this. From negative 1 to 1, my function is this piece facing down, so concurve down. And from here to all the way infinity, negative infinity, function is having this much piece facing upwards. Therefore, it is concave up. Again, from here to all the way positive infinity, function will have again facing up. So, concave upwards. Very clear, right? So, that is there. Now, one more definition. This is about the point of inflection. What does mean by inflection? Inflection is a point, right, where the concavity changes, concavity trend will change, right, at that point. Beyond that point and before that point, you will have two different concavity. So inflection point always will change the trend of the concavity. Okay, so if C is any point of the given open interval, then that point C comma f of C is, point of inflection, right? How? You know now, f changes from upward to downward, vice versa, downward to upward. So if you could see, the trend of concavity at that point changing, so that point is going to be a point of inflection point of inflection. So look at this picture. You see now, this point will, change the concavity trend. So before that point, the trend was concave up. After that point, trend is going to concave down. So upward is changing to downwards, vice versa. Downwards changing to upwards. So those kind of points are now going to be inflection. Inflection point will be like S when write S letter. So the halfway point, middle point is kind of changing the trend, which is inflection point. Okay. So geometrically, the explanation of inflection point is like this, but we need to know, mathematically, how are we going to find the inflection points in terms of calculus? So we have some applications of derivative, right, to find the inflection point. Okay. So now look at this definition. How do you find the point of inflection? Well, this theorem says the point of inflection will occur where second derivative 0 or does not exist. Remember, like finding critical point for the function, right? Go back and check your note 3.2. We found the critical point where first derivative getting 0 or does not exist. In similar way, you could think of finding point of inflection is nothing but second derivative getting 0 or does not exist. So those kind of points are going to be inflection point. In another word, if you are asked to find inflection point, simply find out the second derivative, set it to 0 and look for some x values, or find the points where second derivative undefined does not exist. Okay. So now again, look at this example. So the question is finding all the point of inflection. So we are finding the second derivative. The given function is now polynomial function, very good function, right? So well defined all the way from negative infinity to positive infinity. So we find the second derivative. So the second derivative of the function is now 12x times x minus 2, right? So we look for the points where second derivative getting 0. So if you set it to 0, that means 12x times x minus 2 is supposed to be 0. Now you need to solve this equation for x. Of course, this is gone. So your x should be either 0 or x should be 2. So these are the points, Again, my second derivative 12x times x minus 2 function is well defined throughout the, real line. Therefore, you will not find any does not exist point for second derivative. So therefore, only these two are the possible points where you get, chance of getting a point of inflection. Okay. So after that, so take the entire real line because my domain was entire real line. Negative infinity to positive infinity. Now I have 2 points where getting 0 second derivative, 0 and 2. That means you are going to divide the entire interval into, again, 3 more subintervals. Okay, these are the 2 points. So my first interval is negative infinity to 0, second interval 0 to 2, and third interval 2 to infinity. Again, find some test values. You could choose any values and plugging into your second derivative function and check the sign. Okay, so you are getting what? Second derivative is positive, therefore upward, negative downward, upwards because of positive. So we'll have like this picture, right? So you will have 2 point of inflection here and here. What does mean by that? Concavity trend will change after this point. Yes, true. From here to here, function is facing up, upward trend. After that, downward trend. Again, from here to there, function is having upward trend, right? Therefore, these two are the point of inflection. Make sense, Haley?
Yes, sir.
Yes, yes, good. So remember, we use first derivative test to find whether function has relative max min. Now this is second tool. You could use the second derivative test as well to find whether function has relative max min, right? But I used to prefer to use second derivative to check whether function has a relative max min rather than going for the first derivative. Remember, in first derivative test, you have more work, right? To find whether the function has min max. Remember the steps we followed there for the first derivative test? Just now we had, right? For the first derivative test, you have
Yeah, that
more,
was a lot of steps.
yeah, you have more work. First, you have to find the domain. After that, you chop the domain into subintervals by looking at the critical points, right? After that, you have to test the value for each interval. Then you have to look for the trend where the function has like this, like that, right? For each at each point. So you have more work typically. But second derivative test is very simple. Simple. Only thing is you need to find first the critical points. Find the critical points for the function fx. Okay, point or points. Then simply find the second derivative of the function and plugging those critical values into that function, second derivative function. So if you have a positive second derivative evaluated at those critical points, okay. Suppose if you have second derivative evaluated at those critical points, say you are getting positive, then function is going to be relative minimum. If you have second derivative evaluated at those critical point which is negative, then function has max. That's it. Very easy procedure. That's what this theorem says. Okay, right? So now we have to have some kind of um, tools, I could say, how to connect second derivative, first derivative with the function to identify relative max min. Now you have kind of idea about concavity also, right? Remember, if you want to have the relative minimum function, then function of course have to have concave upward trend. If you want to have concave upward trend, your second derivative is supposed to be positive at that point. That is why checking second derivative positive is enough to get, relative mean. Vice versa. For the relative max, again, if you want to have maximum curve, you have to have concave downward trend. That means your second derivative should be negative at that point. Makes sense, right? So the second method, we are going to find the relative max min, right? So remember, in the problem, they will not say you which one's supposed to be picked. You could pick either first derivative test or second derivative test. That is up to you. Since we are, doing this example under the second derivative test, so I will go for the second derivative for all the problems here. Okay, but that is not mandatory. If you want, you could use first derivative test as well for these all problems. Okay, so now things are very easy. What do you want to do? Yes, if you want to find the relative max min by using second derivative test, first you should know the critical points. So therefore, we need to have the first derivative set it to 0. So these are the two critical values we are getting, 4 and -2, right? Remember, the given function, original function is polynomial function, very good function. So domain is all the way from -infinity to +infinity. Now I got two critical points, 4 and -2. 0 is here, -2 here, 4 will be somewhere here. So let me extend this a little bit. Okay. So my critical points are two critical points. Therefore, my intervals are going to be here. This is to this to that, and that to this. I have three intervals, right? Okay. So now what is our task? Our task is to check only at these 2 points, right? Because we got only two critical points. So function will be either max or minimum at these 2 points, right? So you have to check that. Okay. So we need to know now second derivative as well, because we are going to use second derivative test. Okay. So if you want to use second derivative test, of course, we should know the second derivative of the function. So second derivative function is, this is my first derivative. Okay. So if you want to find the second derivative, well, there are two methods. You could use the product rule to find the derivative of this, or you could expand it, and after that you could just use the normal derivative. It's up to you. So if you do that, you will get the second derivative, which is 6x minus 6. Okay. Now, I'm going to find what kind of, extreme value we get at first point. First, my first point, critical point is now, okay, I'm going for C instead of X. We use letter C for the critical. So my first critical point is -2. I'm going to check whether function has max or min at this point, simply plugging this value into second derivative. Therefore, I'm finding f double prime C, which is f double prime evaluated at -2. Simply plugging here -2 will be -18. So which is negative number. So if you are getting second derivative negative, you will get relative what?
That's a max.
Relative max. Very good. So you will get relative max at which point? At our critical point. But how do you find the function value? What was the maximum value? To find the maximum value, you have to use the function value, right? Simply plugging this critical value into where? Into the original function. Our original function is where? This is our original function, no confusion, okay? Use the original function and plugging that value. So I'm writing here one more time. My original function was x cubed minus 3x squared minus 24x plus 32. But I need to find the function value at -2, simply plugging here -2. Check your calculator and find out this value. So that should be, therefore, there is local max at this point and local minimum at this point. But here I did not mention the value, but you have to find here. So find out this value. What is that? Is -8. Here 4, -12, and here plus 48 and plus 32. This is -20, here gone 12, so you get 60, am I right?
Yes.
Yes. So the maximum value of the function is 60. So if you graph the function, and you will get maximum at 60. So in similar way, you could find the function minimum value. So second derivative test, now you have to plug in second critical point, that is 4. So find the second derivative at 4 now. Again, I'm using second derivative, the same function we have. That's that second derivative. Second derivative, we got 6x minus, that's that. 6x minus 6, right? So 6x, positive, minus 6. So it is positive. So therefore, at x4, you will get relative minimum. So what was the value? So minimum value is going to be my function value, simply function evaluated at 4. Now plugging 4 into function, you should get 4 cubed minus 3, 4 squared minus 24 times 4 plus 32. So that should be 4 cube is 64 minus 16 times 3 is 48. This is 96 and this is 32. Simplify this. So you should get how much it is. So 64, 48 is going to be 16, right? 16, 48. So it is 48 negative, right?
Yes, sir.
Yeah. So that is going to be our minimum value of the function. So you had to find out the minimum maximum like this. So which method is easy? Of course, second derivative is very easy, right?
Yeah, second derivative test is much easier.
Much easier than the first one. Yes.
Right. Okay, so you said the second derivative test is best for relative mins and maxes for
Yes.
finding them.
Yes.
So what is the first derivative test best for?
So there is no particular scenario.
Is that purely for critical numbers?
Yes. Critical. Anyway, for both cases, you need to know the critical points. Oh, yeah. So you are telling is correct. First derivative. So basically, yeah, this is the thing. Once you study both, you will have now more tool, right? So more tool in the sense now you know how to find the concavity. So you could use either second derivative, or if you want now, you could use the first derivative test to identify whether the concavity concave is upward or down. So first derivative test now you could think of, you could use either to find relative max or to find the concavity trend. In that case, yes, first derivative test is useful. So because yeah, you have more than one application. So yeah, but that's up to the student. Some students they feel second derivative is harder than the first, but most of the students they love second derivative because you don't need to draw the picture and checking the trend just before after. We don't need that, right? Okay, so that's it. So this is about finding relative max, min, and concavity. So now let's move to the last section for today. This is finding the limits. Okay, now we are going back to the limit problem, but now we are going to find the limit at infinity. Earlier, remember in chapter 1 and 2, we found the limits for any function at the real value a, right? A is any real value. So this is the one we already, practiced, and we did so many problems in chapter 1 and 2, right? But now, here in this section, we are again going to find the limit of the function value, but where? When x goes to plus or minus infinity. Right now, you will see here infinity. That's why we call limit problems at infinity. So you may have positive or you may have negative as well, right? So if you look at this picture, remember we are familiar with this picture. So the arctangent graph is like this. So you will learn a lot of things about this guy in Cal 2. So for now, you just look at the picture, and this is the arctan graph, right? This is my x value. When x getting bigger and bigger, function is approaching. The function is approaching this line. What is that line? This line is y is equal pi over 2 line, right? So when you extend this pi over 2 line going all the way to infinity, function also will reach there. At this end, when x goes to negative infinity, this is positive infinity. This is negative infinity. Remember, this is my real line, domain x. When x goes to negative infinity, my function is approaching to this line, that is y is equal negative pi over 2 line. Okay, what does mean by that? That means when x goes to either positive or negative infinity, function has one good number, right? Good number, pi over 2 or negative pi over 2. These are the kind of things now we are going to discuss here. Okay. So these are just the explanations and informal definitions. Like earlier we had, so you could go back and check your, chapter 1 and 2, and we had there also two definitions, informal and formal definitions of limit. So in similar way, here also you have two sort of versions of the definitions, informal and formal. Okay, but you don't need to think about a lot with formal definition. I have included somewhere here. So this is just I just included in the note, but we are not going in detail about this. But anyway, you could think of this formal definition with this picture just we had last time, so like that you could think of. But now, what are we going to do? We are simply going to find the limit of the given function at where? At infinity or negative infinity. Again, if you find any form 0 over 0 or infinity over infinity when you evaluate the limit, like earlier, here also we are going to use some techniques to get rid of this kind of scenario, okay, to find the limit, right? So look at this note. Suppose if you find a good number when you find the limit of the function when x goes to in either end, positive or negative, that number, that is my function value, right? Like I explained just now here. So when x goes to infinity, I could rewrite, everything here in terms of the notation, right? This picture says with symbolic form, limit of x goes to infinity of arctan x is, could you tell me what is that answer by looking at the picture?
Pi over 2.
Pi over 2. Function value, this is my function now fx. When x goes to positive infinity all the way here, what is your function value? That is the question. Function is here, graph is here, approaching to y value. Y is my function value. So function is approaching to pi over 2 value. Therefore, this is simply pi over 2. In similar way, when x approaches to the negative infinity this end, then function getting negative pi over 2. Now remember, you are getting two good numbers, right? So these are nothing but two lines. Those lines are, of course, horizontal lines, right? You see? So these lines are called horizontal asymptotes. That's what this definition says. So if you are asked to find the horizontal asymptotes, that is nothing but you are looking for the y value, function value, good number value, real number, where when x approaches either positive infinity or negative infinity. So you are looking for the y values, good values. So that value is called, right? That value with the line. For example, if it is 2, if L is 2, then this line y is equal to is called the horizontal asymptotes of the given function y. Look at this example, right? The given function fx is now 5 minus 2 over x squared, right? If you look at the picture here, what is my limit? X goes to infinity of fx. Look at the picture and tell me, when x goes to positive infinity, function, yes, go ahead.
5.
Yes,
The horizontal asymptote's 5, so that's also
5.
the limit.
It's 5, right?
Right.
Yes. So that means the equation of this line is nothing but y is equal 5. So this guy is now going to be the horizontal asymptotes of this curve. Yes, asymptotes means what? The graph should approach to that line, but not meeting at line. It should approach, all the way, to that line. So since that line is horizontal line, we call that as horizontal asymptote. So it is now clear that if you want to find horizontal asymptotes, you have to plug in either x positive infinity or negative infinity and find out the y value, function value, limit value. Okay. So that is about the horizontal asymptotes. Now we have one theorem. This theorem will make you easy to identify the limit values without picture. If R is positive rational number, rational means what? Could be any real number. if you could write the real number in fraction form, which is rational. So if r is any positive or rational, then limit of c over x to the power r, x could be, any number, but when you approach that x to the infinity, then this answer is of course going to be 0. Makes sense, right? When the denominator getting bigger and bigger, x goes to infinity means denominator getting bigger. So you are dividing some number c by a big number, very, very big number. So your answer is very, very small. So possible smallest number is 0. Therefore, your answer is, 0. So you could use this result to find the limits. Okay. You could think of like, for example, think of finding limit x goes to infinity of say 2 over say x to the power 5. So simply you plugging limit here. So if you use this theorem says that yes, r is now 5 in this case. Yes, 5 is a rational number, very good number, right? So c is now 2. So you could use this theorem now. Simply theorem says this answer is nothing but 0. But remember, this guy is supposed to be positive rational, not with the negative. Okay, no confusion. Theorem says for the positive.
Yes, sir.
Oh, yeah. So now look at this limit. How do you find the limits? Of course, you could split the limit into two. First piece is limit, then second piece limit. Then of course, the constant number limit is always the constant number. Now again, you could use the theorem to this piece. So like I explained here. So this limit is going to be now 0. Therefore, that is 0. 5 minus 0 is 0. Oh, sorry, 5. So answer is 5. Okay. Yeah. That means what? That means when x goes to infinity, the function is approaching to 5. Therefore, 5 should be a horizontal asymptotes for that function, 5 minus 2 over x squared. Makes sense. Okay. Right. So now these are the techniques you could learn to find the limit at infinity, right? So how do you find this problem? You see now, if you plug in limit right away to this function, 2 times infinity minus 1 over 2 times, infinity plus 1. Remember, infinity means very big number, right? So when you multiply infinity with very big number, again, you will get big number, very, very big number. So compared to that number, 1 is nothing. Therefore, this is very close to, infinity, right? A very big number, right? So again, infinity, you are adding 1, again, you are getting very big number infinity. So if you plugging limit directly to this problem, you are getting infinity over infinity. So it is undefined. So you have to use some techniques to find out the limit value. Okay. So what kind of techniques we use? We'll look at this problem. So you simply divide everywhere by x. Okay, so simply divide everywhere by x. Divide this guy x, divide this guy by x, divide this by x, and divide this by x as well. So you will come up with this, right? 2 minus 1 over x over 1 plus 1 over x. Now plugging the limit will give you good number. When x goes to infinity, 1 over infinity, what is this one? When x goes to infinity, you could use that theorem, 1 over infinity. Remember, 1 over infinity and 1 over negative infinity is always 0. Okay? So when plugging x infinity here, this is going to be 0. This is going to be 0 as well. Therefore, answer is 2 over 1, which is 2. Okay? That is very easy now. Finding limits. Okay. Now look at these guidelines. If you want to find the limit at infinity or positive negative infinity of the rational functions, what does mean by rational functions? Rational functions means you may have two functions, one is in numerator, another one is in denominator. Okay, with the the degrees are the rational numbers. If this is the case, then what are they telling? Follow these steps. If the degree of the numerator is, the degrees of the polynomial, right? Degrees means what? Degrees means nothing but degrees of the numerator means the highest power of the variable x. you may have any variable, but for instance, say x. So the highest power of the numerator is called the degree of the numerator, right? Vice versa for the denominator also. So what are they telling? If the numerator degree, if the highest power of the numerator is less than the denominator power, then the limit of the rational function, or limit of the given problem is always 0. Okay? That means what? If the denominator have the higher value than the numerator, then it's going to be always 0. The numerator and denominator having same a degree, then the limit answer is nothing but the ratio of the leading coefficient. What does it mean by that? I will explain one problem with the second scenario. Okay. Suppose if you want to find the limit x goes to infinity of say 2x squared plus 3x minus 1 over say x squared plus 5x minus 1. How do you find this limit? Remember now, you have like a fraction. So what is the degree? What is the degree of numerator?
2.
2. The highest power of this expression is 2. Here also you have 2. That means now, degrees are same. What are they telling? If the degrees are equal, right, the limit answer is nothing but the ratio of the leading coefficient. Leading means the highest power coefficient. Here highest power is x2, the coefficient is 2. Here the highest power is x2, the coefficient is 1. Simply 2 over 1. That will give you the answer, which is 2. Makes sense, right? So that is my second scenario. The third scenario says what? The degrees of the numerator is higher than the denominator. Then answer is always going to be does not exist, infinity. Okay. For case 3, problem will be like a limit x goes to infinity of 3x cubed minus 1 over say 2x squared plus 1 plus x. Now if you look at this problem, this is exactly my third scenario, right? The degrees of the the numerator is now 3, degree of the denominator is 2, so this is now higher, so answer is always does not exist. In another word, infinity, or does not exist. Okay, that means what? If you have highest power in numerator, answer is the infinity. If you have highest power in the denominator, answer is 0. If you have the same power, then just the ratio of the leading coefficient is going to be the answer. All 3 scenarios are here. So you could go for the problems here and simply write down the answer. Now you have all the tool, right? You will tell me, even though this problem is kind of complicated, if you apply these guidelines, answer is straightforward, just one word answer. Look at the degree of the numerator 2, degree of the denominator 5. So 5 is the highest one, therefore this guy is having highest power, answer is always 0, even though you have big numbers here. Okay? Or you could divide by the highest power x to the power 5 here and there and do the things, and you will get the same answer. What will happen? Suppose if you are given a square root, of course, now if you are having square root, we will be in trouble. Okay? So now tell me, what is the degree of the denominator now?
Isn't it 1?
It is 1, because you cannot say now 2, even though you have here 2, but you have square roots, so always you have to apply this power into that degree. So even though you have 2 here, right, you have x squared, but once you take the square root of x squared, you will come up with x terms here, right? So you will get x terms, therefore the degrees is ultimately going to be the same degree whatever you have outside. So that means degrees of the denominator and numerators are same, right? Same. But the thing is now you have to play around a little bit to find out, because you have here now square root operation, right? Therefore you have to think a little bit and make sure that you understand. So what are they doing? They are simply dividing by x here and there, right? So what are they doing here? So simply dividing everywhere by x, because my highest degree is x to the power 1. So simply divide by x everywhere. Okay. So now I'm going to divide this entire square root by x. This is happening actually. So now if you simplify, you have now limit x goes to infinity. Now if you simplify this will be limit x goes to infinity. Of course, this guy is going to be negative 10. This is okay, 6 over x. Okay. Here you will get 1. Okay, now the catch is, how are you going to divide this inside function by x? Remember, you have the inside function has square root, this high doesn't have. So what I want to do, I want to make here also square root to match up with this square root, right? Therefore, I am creating here square root, right? X could be written as square root of what? So I am replacing x by square root x squared. Why I am writing like this? Because to match up with this square root, because I'm going to move this guy inside this square root. Okay, so now this will be simplified to negative 10 plus 6 over x. Now I am going to move everything under one square root. You see now? Because both of them have now square root. I could do that now easily. That makes sense? Now you could apply, you could plug in infinity here. What will happen? So if you're plugging infinity, 6 over infinity, this guy is going to be 0, right? Plus, okay, now tell me, when x goes to infinity, what will happen here? When x goes to infinity, you could think of this as a new problem. Remember, now degree is here 2, degree here as well 2. So you have same degree. So answer is simply 16 over 1, but that is inside the square root. Therefore, limit of that guy is square root 16. Okay. So now this is what happening actually here, but I have written here just simply one step, but you should get understand better. When you do more problems, you have so many, scenarios, and you will figure out everything in easy way. Okay, so I will include some more exercise problem in my workout, class notes. At the same time, please work through these problems and make sure that you understand everything before coming test.